Chapter 4.1. In Chapter 4, we begin our discussion on probability. So if you'll notice, I've highlighted the definition of probability. It is a numerical measurement between 0 and 1 that describes the likelihood that an event will occur. Some things I want to point out. One is that you are translating this into a numerical measurement. An example of this would be like the weatherman when they tell us the chance of rain or snow. What they've done is they have taken an event of rain and they have converted it into a numerical measurement for the likelihood that it will occur that day. Now, the other thing that you need to remember about probability, and this is extremely important, is probability will always and only be a number that is between 0 and 1. So if you'll notice, I've created a number line here, and I've highlighted 0 and 1 and everything between. Anytime you do any calculation, when it is asking you to calculate the probability, you will always get a number of 0, 1, or anything in between. So if you are asked what is the probability of, and you do your calculations and you get 2.98, you're wrong. It can only be a number between 0 and 1. So please get that stuck in your head that when you are asked the question, what is the probability of something, that your answer can only be a number between 0 and 1. Now, it can be 0. When the probability of a particular event is 0, that means it cannot or it's impossible, it will not occur. The probability that it will snow today is 0, that means can't happen, won't happen. Probability can also be 1, and that means that it will 100% occur. So the probability that it will snow today is 1, that means there's a 100% chance of snow, which can occur. Now, in your book on page 140, number 12, I've put that problem here in the notes, and it gives us 4 values, and it asks, could these be probabilities, yes or no, and if so, explain. So if you'll notice, the first one is negative 0.41. Well, no, that cannot be a probability. Why? Because it is a number less than 0. Therefore, that tells me right there, probability will never, ever, 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 ever be a negative value. So if you're calculating what is the probability of, and you get a negative value, you need to recalculate. It will never be a negative number. B says 1.21. Well, no, that is not a probability because that number is greater than 1. So anything larger than 1 cannot be a probability. Now in C, it's written as a percentage, 120%. Well, what numerical value is 120%? Well, that would be 1.2. So no, that is not a probability either because, again, it is a value that is greater than 1. And then the last one is 0.56, and the answer to that is yes, it can be a probability. Why? Because 0.56 is a value that is larger than 0 yet smaller than 1, so that fits the criteria. When we're dealing with probabilities, one of the things that you might be asked to do is to create what is called a sample space. Your sample space will always be the set of all possible outcomes. So it depends what the event is. And how we write that is capital S equals, and then within brackets we list all the possible outcomes. And we'll do that here in a little bit in an example. Now, to actually calculate the probability, this reads the probability of an event. It could be the probability of rain, the probability of snow, whatever your event is. How we calculate that is in fraction form, and on the top or the numerator is the number of favorable outcomes, and the denominator or the bottom is the total number of possible outcomes. So how would we write that? The probability of an event is F for favorable outcomes over N, which is all possible outcomes. F over N, if you recall, we did that calculation in Chapter 2 in the frequency table. It was our relative frequency, F over N, and it gave us a decimal. And that's what we're looking at, a decimal that is between 0 and 1, so F over N. Now, you can leave your probability either in fraction form or a decimal. Typically, I believe when you do these problems, or homework problems on the computer, you'll probably have to put it in decimal form. All right, the definition of equally likely, when events have an equal chance of occurring. So if I said the probability of rain is 50% or 0.5, well, the probability of it not raining is 50% or 0.5. So they each have 0.5 as the probability. Those are equal. That's what we call equally likely. There's a good guided exercise in the book that you'll want to look at. And then here is an example. So here's the event. The event is that we're going to flip a coin. So the first thing that I have done is I have written the sample space. The sample space again is listing all possible outcomes. Well, when you flip a coin, what are your possible outcomes? You could get heads or you could get tails. Okay, so the event is flipping a coin. Here are my possible outcomes. So then what I'm going to look at is finding the probability of when I flip a coin that I get heads. And then I'm also going to find the probability that when I flip a coin I get tails. And this is where I will use F over N, favorable over possible. So when I flip a coin, what is the probability I get heads? Well, how many favorable outcomes are there on a coin that is heads? Well, one side of the coin has heads. And possible outcomes is 2 because there's 2 sides to a coin. So the probability of getting heads is 1/2 or 0.5. Probability of flipping tails. Well, again, there's one side that has tails. There's 2 sides to the coin. So it is 1/2 or 0.5. Now, these events would be what we call equally likely because they both have the probability of 0.5. On the next page of notes, we're going to look at another example. And this is where we roll a 6-sided die. So just a regular die that has 1, 2, 3, 4, 5, 6. So the sample space is, in brackets, all possible outcomes. When you roll a die, you could get the number 1 through 6. So this would be what I call my sample space. Then right here I have what reads, what is the probability that when I roll a die, I get a 4? So I need to ask myself, what is the favorable outcome? Well, there is 1 4 on the die, and there are 6 sides to the die. So the probability of getting a 4 would be 1/6. Over here, what's the probability of getting a 3? Well, there is 1 3, and there are 6 sides, so 1/6. If I were to find the probability of each of these, we've already found the probability of getting a 3 or getting a 4. Well, the probability of rolling a 1 would be 1/6, 2 would be 1/6, 5 would be 1/6, 6 would be 1/6. So again, here's all my possible outcomes. Each has a probability of 1/6. They would be considered equally likely. Then you could also be asked different questions, such as the next one, which reads, what is the probability of getting an odd number? So I look up here, I have 1, 2, 3 favorable outcomes that are odd, 6 possible sides, so 3, 6, or 1/2, or 0.5. Now, if you do leave your answer in fraction form, be sure that you reduce the fraction. Do not leave it as 3/6. Then, sorry, my phone's ringing, but I'm going to ignore it. Then we have, what is the probability of getting a number that is greater than 2? So I look in my sample space. All numbers that are greater than 2 is the 3, 4, 5, and 6. So there are 4 favorable outcomes out of 6 possible, 4/6, or 2/3. Here we have, what is the probability that when I roll a die I get a number greater than 10? Well, I look up here, there are no numbers that are greater than 10. So the favorable outcome is 0 out of 6 or 0. So it cannot happen. Here I have, what's the probability that I roll a number that is less than 9? Well, all of these are less than 9, so we have 6 favorable outcomes out of 6 possible, or 1. So that gives you an idea of what we're looking at on probability. Now, here is another example. Here we have, where we're going to flip a coin 3 times. Now, what you need to realize here is one event is 3 total flips because we're going to flip the coin 3 times. So when I created my sample space, I have to look at all the possible options that occur when I flip a coin 3 times. So one possible outcome is that I get heads, 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 tails, tails, tails. If I flip it 3 times, I could get heads and then tails. So I've listed all possible outcomes, and if you'll look, there's a total of 8 possibilities that can occur. So what you might be asked is, what is the probability of getting all heads? So I look up here my possible outcomes. This is the one that is all heads. So there is 1 favorable, 8 possible. So the probability of getting all heads is 1/8. Here it reads, what is the probability of getting exactly 2 tails? And this is where you have to be careful because of the word exactly. Here I have 2 tails. I actually have 3 tails, so that's 1 too many. I want the ones that are only 2. So there's 2 tails, there's 2 tails, and there's 2 tails. So this would be 3/8. Now, we've already talked about one characteristic of a probability is that when you calculate a probability, it has to be a number between 0 and 1. Here is something else that you need to watch for. This reads, the sum of the probabilities of all simple events in a sample space must equal 1. Here's what that's talking about. The probability of getting this, all heads, is 1/8. The probability of getting tails, tails, tails is 1/8. If I were to calculate the probability of each of these, I would get 1/8 for each. When I add all of those up, I would get 8/8 or 1. Here we already talked about each of these would be 1/6. So if you were to add up the probability of all of the possible events, you would get 1/6. Here, probability of heads was 1/2. The probability of tails is 1/2. We have 2 possible outcomes. I add their probabilities, I get 1. That should always occur. Now, so far in all of our examples, our events have been equally likely. So I want to show you an example that does not always occur. It says, in a bag there are 4 red chips, 2 green chips, and 3 yellow chips. So here's my attempt at a bag. R represents the 4 red chips, the 2 green chips, let's see, there they are, and then the 3 yellow chips. Now, notice my sample space, I have red, yellow, green. Now I want to point out you need to be very careful on a sample space such as this, because if I leave my sample space as is, it appears as though, probability of a red chip is 1/3, yellow 1/3, green 1/3. They're equally likely, and that is not correct because there's obviously more red chips. So when I have values that are not the same, I in some way want to place the number. So I'm going to put that there's 4 red. Let's see, I put yellow first. So there's 3 yellow and there are 2 green. So I some way want to show or indicate that those do not have an equally likely probability. So now that I have my sample space correctly set up, I'm going to come over here and calculate the probabilities. What is the probability of getting a green chip? Well, I look in here, there are 2 green chips, so there's 2 favorable outcomes out of how many chips are in the bag. Well, that would be adding 4 plus 3 plus 2, so it would be 2/9. What is the probability of getting a yellow chip? Well, there are 3 favorable yellow chips out of a total of 9 chips. And again, 3/9 would be 1/3. And then the probability of getting red would be 4 red, 9 total chips. Now, this reads, are these events equally likely? Well, 2/9, 3/9, 4/9, no, they're not the same number, so they are not equally likely. Now, the two characteristics of probability that I want to make sure of is one, that all my calculations are a number between 0 and 1, which 2/9, 3/9, and 4/9 are all a number between 0 and 1. And then the second thing I want to ask is, I have 3 different color of chips, so do my probabilities of all possible outcomes add up to 1? Well, 2/9 plus 3/9 plus 4/9 is 9/9, which equals 1, so I know I'm okay there. Now, sometimes you will be asked a question or a probability such as this. What is the probability of drawing a chip that is not green? Well, I look in the bag. How many of those are not green? Well, 7 of them are not green out of the total 9 of them. Now, not green means yellow-red, so 4 plus 3 is 7. Or not green, there's 2 green ones, so you could take 9 total chips minus the 2 green ones, and you're left with 7 of them that are not green. Now, that leads me into talking about the concept on the next page of notes, which is the complement of an event. So before I go over to that page, I want to kind of use this as my guide. The probability of green and the probability of not green, these are considered complements. The probability of rain, not rain, those would be complements. The probability of snow, not snow, would be complements. Now, if you'll look on the next page of notes, this is an extremely important concept as well. The probability of an event added to the probability of its complement is always 1. So, if you look here, the probability of green is 2/9. If I were to add that to its complement, not green, which is 7/9, you add 2/9 plus 7/9, you get 9/9 or 1. And that will be very helpful as we continue on calculating probabilities. So that's the introduction to complements. Now, if you'll look, where this will eventually be helpful is if I'm looking for the complement, I can always do 1 minus the probability of that event. Because if you algebraically solve this for the complement, you would subtract the probability of A from both sides. And here's where that works. On the previous page, we did the probability of not green. Well, since that's a complement, I know I can actually calculate 1 minus the probability of green. So I could have done 1 minus, and the probability of green was 2/9. Well, you need common denominators, so you do 9/9 minus 2/9 is 7/9. So that will be helpful as we continue on and get more in-depth probability problems. All right, so let's take the information we've learned about probability and now apply it to an application problem, because that's ultimately what you're going to need to be able to do. So our example, you work in a hospital which must be staffed 7 days a week. Each week you get 1 day off, which is randomly picked by your supervisor. Suppose 1 day of the week will be randomly picked as your day off for next week. All right, so we're talking about getting a day off of work, which I know we all like. So our possible outcomes are the days of the week. I could get Monday off, Tuesday off, Wednesday, Thursday, Friday, Saturday, or Sunday. I get one of those days. So my sample space is all the days of the week. Part B reads, find the probability you will have a day off on the weekend. So I would write that as the probability weekend, because I always label my probabilities. I don't just give a number answer only. I always want to see that you label it. So the probability of a weekend, so I'm going to do favorable over possible. So I look up here, which days of the week are my weekend? Well, that would be Saturday and Sunday. So there's 2 days out of a possible 7 days in the week. So it would be 2/7. Then C reads, find the probability of not the weekend. Well, these are what we call complements. So now I'm finding the probability of not weekend. And there's two ways in which you can find this probability. You could go, oh, 1, 2, 3, 4, well, Monday, Tuesday, Wednesday, Thursday, Friday are not the weekend, so 5 of the 7. Or, since we'd already calculated this, you could have done 1 minus the probability of weekend, and 7/7 minus 2/7 is 5/7. And then again, the weekend is 2/7, not weekend is 5/7. These are complements, therefore, when you add these up, they should add up to 1, which they do. All right, let's look at the next one. A spokesperson for United Airlines said there is a growing demand among flyers for special meals, vegetarian, low-fat, etc. Out of 60,000 meals they serve every day, 6,000 are special. A passenger is selected at random and asked to select a meal. So the type of meals is my sample space. So I've created the sample space so there can be special meals and there can be regular meals. Now, here's an example where you need to be careful. If I leave my sample space as it reads, it appears as, oh, half of the passengers get special meals, half of them get regular, and that is not correct. They tell me 6,000 of them are special, so below this, I'm going to put 6,000, so I know 6,000 of them are special. Well, how many of them are regular? Well, if they serve a total of 60,000, 60,000 minus 6,000, this would be 54,000. Now when I look at that, I'm like, okay, these are not equally likely because obviously more people get a regular meal. All right, part B, find the probability the person orders a special meal. So I'm going to label this the probability special. How many favorable outcomes? There are 6,000. How many possible? 60,000 that were served. So I'm not going to leave that as a fraction because it needs to be reduced. You can reduce it to 1 over 10, or you can just put 0.1 if you were to go to your calculator. Now again, it's a number between 0 and 1, so I know I'm okay. Part C says find the probability of not a special meal. So it's going to be probability of not special. Now, right off the bat, again, I recognize that these are complements. That makes this very easy. If these are complements, then these two should add up to 1. So since we've already calculated this probability, I can just do 1 minus 0.1 and say that probability is 0.9. Now, you could also calculate that probability as how many favorable outcomes are there? 54,000 were regular meals or not special out of 60,000. And if you go to your calculator and divide that, you would get 0.9. Both ways are correct in calculating. I don't care which way you choose to do it. Now, the last example is using information from a given chart. It says a poll of 1,000 couples conducted by Bruskin and Goldring Research for Corbel Champagne Cellars gave the following information. Okay, this is the length of dating time before engagement. So you have 200 couples that have been dating but have never been engaged. You have 240 couples that have dated less than 1 year and then they got engaged. 210 that dated 1 to 2 years before they got engaged, and then 350 that dated more than 2 years and then got engaged. Now, notice I have my summation here, and that's going to be important because that's what gives me my denominator and my F over N. So I'm going to add those up, which they already told me it was 1,000, so That made it easy. Had that not been given, though, you just add those up. So I know I have 1,000. Now, the first thing it asked me to do is to list my sample space. Now, my sample space is all possible outcomes. So if you were given this questionnaire, what are the possible outcomes that you would check? Well, you would say you've either never been engaged, you've been engaged, or I'm sorry, you're never engaged, you've dated less than a year before getting engaged, 1 to 2 years, or more than 2 years. Now, again, be careful here, because if I leave it as such, I'm thinking, oh, 1/4, 1/4, 1/4, 1/4, and that's not true. Because never engaged, there were 200 couples. Less than 1 year, there was 240, 210, and then 350. So now I can look at that and go, oh, these are not equally likely. Now, part B says find the probability that a couple is engaged for each amount of time. So, in essence, this is asking us to find the probability of each one of these. So we're finding the probability of all possible outcomes. So the probability of never engaged, how many favorable outcomes? 200. How many possible? There were 1,000 couples, so that would give me 0.2. Now what's nice is this comes out to nice, neat terminating decimals. The probability of less than 1 year is 240 couples out of 1,000, so that would be 0.24. And then we have 1 to 2 years. So 1 to 2 years, that's 210, 0.21. And then we have more than 2 years. So that would be 350, or 0.35. So there's the probability of each possible outcome. So as you can see, they are all numbers between 0 and 1. They are not the same number, therefore these events are not equally likely. Then the last question is, do the probabilities add up to 1? Well, if you add 0.2, 0.24, 0.21, and 0.35, yes, they do. Should they add up to 1? Yes, because they are all possible outcomes which should always add up to 1. All possible outcomes should always add up to 1. So the answer to that would be yes. That completes 4.1.